Okay, so last time we talked about work. We talked about a very simple formula, which is basically W equals F times D. Work equaling the force times the distance. And I gave you an example where a box was being slid across the ground. Of course, it's frictionless ground to a new location, and that if I multiply the force at which is being pushed times that distance, I would figure out the amount of work done when I got to this new location. However, this is a very ideal situation. But we realize that there's always, there's some friction involved here, which is not in this case. And there's also maybe gravity or the direction in which I'm pulling it. I mean, there's lots of situations that this situation could happen, but not necessarily this pretty. Therefore, I wanted to give you an opportunity to see two other cases here where it can actually be a little different. It's not difficult, it's just the same thing, but you have to put a little bit more thought into it. My situation I want to give you for the first would be a box. And if we wanted to lift that box upward, we know that we would have to do it at least with the amount of force to counteract that of gravity going downward. Let's imagine that this box is 10 kilograms. Now our 10 kilogram box, we want to lift it up, but gravity is pulling it down. Now we can figure out the force we need at least by doing our formula for Newton's second law. Force equaling mass times acceleration. In this case, we know that the force will equal the 10 kilograms of the box times 9.8 meters per second, which is the acceleration due to gravity. So we know that the minimum force needed to lift this box is going to be 98 newtons. Okay, well, now we know at least the minimum force needed here. And let's use that minimum force to lift this box. Say we are lifting it up at a constant acceleration. A constant velocity. And we're lifting it up on a pulley, and there's a rope that goes down this way, and we have our guy over here. I love my guy, and he's pulling backwards on this rope here because he really wants to lift this box up at a constant velocity. And what he's going to do is he's going to lift it up, and let's say he lifts it up to a height of 4 meters. Now our height here is going to be the same thing as distance. I mean, he's moving it from here to here. It wouldn't be any different if he was moving from here to here. It's just height, as we generally call upward. And we want to use the same formula as before in order to determine the work done here. So work is equaling the force times distance. Now, although he's pulling this direction on the rope here, it's basically being redirected by this pulley. But he's pulling up with the force, the minimum force of 98 newtons. So the work is equaling his 98 times the 4 meters he wants to lift it up. And so once he lifts it up those 4 meters, the work he has completed in doing such would be 98 times 4, which is going to come out to be 392 joules of work. Now, that is a very simple problem, just change in a different direction. But what I'd like to do is take this a step further and discuss in terms of vectors if the box isn't being pulled in the exact direction of where we want it to travel. So let's imagine this instead, a box. And we want it to travel to this new location right here. We know the distance from here to there. Let's call it D for now. And instead of us actually pushing it or pulling it from behind in the exact direction that we're trying to get it to, let's imagine that we were instead pulling it upward with the force of, let's just say, 10 newtons to this new location. Now, it would not be right for me to do simply F equals, or work equaling F times distance in this case. I mean, it still is that formula, but what we need to consider is the force in the direction of travel. This part right here. We need to incorporate this part of the force over this distance in order to determine how much work is done. So let's put a little trigonometry in here, and we realize that what we're going to find out instead is that work is equal to force times distance times cosine theta. Theta being the angle in that location there. Now, I could put the cosine anywhere in this formula here. It just doesn't matter. But if you really want to get the nitty-gritty or be stiff about it, you could put this cosine right here, only because we know that we're trying to find the cosine theta of that force. So let's try an example here. In our example, let's try to imagine that this distance is going to be equaling 10 meters. And we have our angle here being our theta equaling, let's just go with 45 degrees. Well, we have to do ourselves a little bit of trigonometry, or we could just plug and chug. In this case, we're going to go W equaling force equaling 10, distance equaling 10, and cosine of 45. So work is equaling 100, and cosine of 45 is equal to 0.70. So if we multiply this through, we're going to find out that the work being done is going to be 70 joules of work. Now, that example I kind of just put together for you, but let's try another one where we can actually see how this comes into play on this, and not so conveniently. So our last situation I'm going to give you guys. Here's a box. We want to push it up on this inclined plane here to a new location. And on this inclined plane, instead of actually pushing it in the direction of travel upward, we're going to push into it. And we need to figure out, well, how much force is actually being applied in the direction of travel. In our direction here for distance, let's go ahead and use, let's go 18 meters. And in this case, let's pretend that I'm actually using, let's say 9 newtons of force here. And we need to take in consideration that that is actually being pushed at a certain degree off of the direction of travel. In this case, let's consider theta to be 36 degrees. So now we have some really odd numbers. I see that I do have some multiples here, but that wasn't done intentionally. So if we use our basic formula like we did before, work equaling force times distance times cosine of theta, we can plug and chug. 9 times 18 times cosine of 36. Work equaling 162 times 0.80, and our final work product will be 131.06 joules. I hope that is easily done and understood, and I thank you for watching.